Okay, so yeah, welcome back everyone to the Formal Methods for Software Engineering lecture. We talked about different places in industry where formal methods are used, and we looked at some of the very big players in formal methods in research and also in applications. And yeah, we looked at, well, obvious ones and historical ones like NASA, where formal method groups were founded and where the terms were basically proposed and defined. Then Facebook, where they use, um, yeah, where they use it at large scale. Then we looked at Amazon, at Microsoft first, that have the Z3 solver, which is also one of the tools that we're going to use, and Amazon, where they have to make sure that their web services run smoothly, and they basically work a lot on critical infrastructure. So they have used some different formal methods tools to make sure that their infrastructure works well. So they use, of course, also some analysis based on code, but also you will see that a lot of the formal methods tools, they're also for, let's say, conceptual modeling, or first making sure that you describe what do you want your system to do, then you analyze the properties of your system before you even implement it. And then, of course, there's this step of automated implementation. I think they haven't used it here, but they reported on some case study where they have used TLA plus, which is another little bit more complex formal methods tool. So there's kind of a hierarchy in complexity of formal methods tools. And I think that most of the things that we're going to do, they will not have the complexity of this TLA plus. You can also do simple things with TLA plus, and you can also do very, very complex things. So some people, they give maybe just a complete module on just this one tool, TLA plus. So for this module that I'm teaching here, I decided to give you a bit more broader overview of different tools that can be used, and you can then maybe from there see how do they compare to other tools on out there, and in what way can you use the new tools. So by giving you a good variety overview of the different tools, hopefully you can then adapt to other tools more easily. So basically there they use TLA plus to define some of the protocols and infrastructure in their web services, and they report on how it actually helped them to build better software. And yeah, they use also all kinds of other systems because it's just, yeah, so complex what they're dealing with. So one of my colleagues, he is, for example, has been working on some system to analyze just the policy rules. If you have some access systems, you might have to define some policy rules, who is allowed to do what. And then there are security, or there are basically attacks in terms of security, where somebody tries to do things that they shouldn't be able to do. And they wrote a tool for some Amazon Web Service configurations that tries to check them for potential security breaches. And they used the Z3 solver of Microsoft that we just saw on the previous slide. So somehow it's all connected. And one of the lessons that they described in this paper, where they use TLI plus, that modeling the design is actually quite valuable. So we will also do basically both sides of the of this medal. We will do the modeling, where we actually learn about our system, and then we will also use the tools to automatically solve parts about our system. So you will see the in terms of the exercises, we will do both some more handwritten, where you write stuff down to reflect on it, and then some other stuff more automated, where you translate stuff to a problem that then you want to be solved. So basically, the computer will find the solution for you in the second case. Yeah. So there are usually the main factors that need to be looked at, especially when you have systems that should run for a longer time. So when you have kind of reactive systems that take an input or read inputs from the environment and then process them and put some output back to the environment, but do this over a longer time. So for example, everything that runs on the web, Usually, it's not just one input and one output that is generated, but it has to interact with other services over a long time. And then you have two main properties that people look at. So these are properties where we already look into a, let's say, temporal aspect, because we not only have the input and output, we also have the time where this input and output happens over time. This is something we will look into really more detail in the second part of the module. We will look at temporal aspects. But when you have temporal aspects, there's usually the safety. So what is the system allowed to do, or what is it not allowed to do? And then you can find safety violations where actually at some point in time the system did something it wasn't allowed to do. And this is one aspect. The other aspect, which is slightly different, is the liveness aspect. What the system must eventually do. So this eventually, has anybody here been in the generative software engineering lecture? No, because there we also have a part which actually relates to automatically synthesizing reactive systems from temporal specifications, and there we also have a liveness part. So basically, this liveness part is that the system must eventually maybe complete something. It must eventually answer to a request. How is that different from what the system is not allowed to do? If I would say the system is not allowed to ignore a request, is that the same as the system must eventually answer to a request? Sounds very similar, right? But here in the safety, it's something that is observable immediately. So if I say my system is not allowed to ignore requests, this means it would have to immediately tell me I'm ignoring this request. Or to detect that it has ignored it, I would have to know immediately it's not going to respond. But that's not really realistic for, let's say, some web service. Some web service might take a request, and then it might take some time until it responds. So there's no immediate observation that something was violated. So how do you know that a web service violates a liveness property? Let's say you wait 5 minutes and it didn't respond yet. Is the liveness property violated? Who says yes, the liveness property is violated if the web service didn't respond within 5 minutes? Why? Who says no? And why? Okay, why do you say no? It could respond after 6 minutes, right? And we don't know. So that's the tricky bit about the liveness properties. Because how do we know that they are violated? We have to wait for how long? Infinitely long, right? So to observe that a liveness property has been violated, you either need additional knowledge or you have to wait infinitely long. If you would have the additional knowledge that a request only has a lifetime of, let's say, half an hour, and then the session is terminated, you would know that maybe after half an hour, you have a detection of the liveness property, but of the violation of the liveness property. But usually, it's more tricky, and you can't put a time bound on this. If you can put a time bound, people can argue that, well, then it becomes a safety property. So usually the liveness properties are the tricky bits, and we will see how to handle them. So there are special cases where it's possible to handle them, but they usually require abstracting away a lot of information about your system. So really boiling it down to some core constraints that you can handle. And we will do that in the basically the last quarter of this module. Because, yeah, the timing stuff is always a bit tricky, and we need all the other stuff before that to understand this. Okay, yeah, there are many more. So there are some success stories of formal methods, tools. There are some papers about applications in industry. I think France is doing a lot in terms of railway traffic with formal methods. So there are some ongoing projects funded by the government over there to secure the railway systems. or to make sure they are safe, stuff like that. Then there's this big distinction between hardware and software. So we say here it's formal methods for software engineering. There's also formal methods for hardware, and I think it also originated from hardware. For example, from chip design, people apply lots of formal methods there because if you want to print some circuits and produce them in scale, you want to make sure that the hardware circuits that you build, that they really work well under all the circumstances that you could think of. So for example, Intel uses model checking along with simulation and other kind of techniques to detect issues in the hardware design. There was some historic, I think, some multiplication bug in some Intel processors where people then have, retroactively used formal methods to track it down. But this was only after it was discovered in the wild. And that's always very tricky because then you have to replace CPUs basically. And some other companies, they develop their own in-house model checkers. So do you know other companies that maybe make very complicated circuits and chips? NVIDIA, yeah, exactly. So they have, of course, some cooperations with other big verification companies, but they then pay those companies money to build the tools exactly the way that they want them. So NVIDIA has their own kind of formal method tools that then only NVIDIA is able to use. Okay, and then for software design, it's been traditionally not that much because people always considered it not as critical, right? You can easily change software. You just, I don't know, put a USB stick in and update it. But yeah, it's been also now with moving to cloud computing and things like that, people realized, yeah, we also need formal methods actually for developing our software because it's increasingly important to have good working, well-working software. So there are some, let's say, widespread perceptions that formal methods and formal analysis is very costly. And it is true that it's more costly to do a formal analysis and to apply formal methods tools than it would be to just hack some code and hope for the best, right? There's always this kind of trade-off. And one other thing is let's say the teaching and education, because if you have lots of developers in your company, none of them know formal methods, then it will be very, very difficult for your company to employ formal methods tools, right? But there are some, communities that say we need to maybe change this so that it's cheaper for companies to use formal methods tools. And then what comes out is this like a module on formal methods for software engineering so that people can be educated on these tools and then see, is it worth using them in the company, and they could be maybe part of the adopters, right? And then, of course, there's the scalability issue. So we will see some of these tools, they have a very high complexity in terms of the running time that it takes the tool to solve a particular problem. And yeah, some other ones, they don't suffer from this. So a lot of research, I think in particular at Facebook, for example, and also at Google, they look at how do you scale those methods? How can you make sure that they just run in the background? So now in your almost any IDE that you have, there are some static analysis of your code that can analyze issues in your code and tell you possible problems in your code. So these are based on formal methods that people have put a lot of work in to make them scale and to just let them run in the background on your normal computer, right? Yeah. So one of the maybe challenges is that for hardware, you have all these design languages like VHDL, Verilog, that some of you might have used. Who use these hardware design language, those chip design languages like Verilog and VHDL? Yeah, some of you. I also did this in my studies a long time ago for some circuit design. So it's more standardized there than it is, for example, in software. Like, what are the design languages we use in software? How do we describe a design of our software before we implement it? So the implementation languages, yes, that's maybe Python, C++, C#, Java, stuff like that. But what are the design languages in software engineering? Anybody has an idea? There's stuff like the UML that people use for software design, but the UML itself has 13 different languages in it: class diagrams, activity diagrams, state machines. So in software, we don't really have this design language that everybody uses. And well, everybody uses maybe some slightly different environments. So there are a little bit more challenges to apply to software engineering than to hardware engineering. Okay, so let's go back to the interactive part. We already had this question. That one we had as well. And then this one. So for hardware, yeah, what are we going to analyze? We're going to analyze the circuits that we're going to put on the silicon, right? But what are we going to analyze for software? What kind of software artifacts might we analyze with formal methods? So you can just put one or two, or doesn't have to be exhaustive. So we will get it exhaustive by everybody answering. So these software artifacts, this could be anything, created during the software development process or the software runtime. Okay, so yeah, so let's see. So here, mathematical models or UML. Yes, we can create mathematical models of our software, and we can create UML models of our software, and then we can analyze them. So there's a bunch of works that look at how can we analyze class diagrams. How can we check that models can be instantiated from this diagram? There's, for example, the object constraint language, which makes it, well, tricky to constrain your systems. So then you want a formal methods tool that tells you whether you did something wrong or not. Then requirements. Yes. So the thing is, to apply formal methods tools, you have to bring the requirements to a certain format. So you have to, maybe you want to look at conflicts between requirements. You can do that, but only if you formalize the requirements in some way so that you can analyze them with a machine. So there are different works that maybe try to extract natural language requirements, try to formulate them into some constraints, and then try to analyze those constraints. So that's one thing. And there's actually one of the examples that we will have for the model checker. So for the fourth tool that we're going to use, there people have, which is somewhat like requirements, they have actually formalized contracts in formal methods to analyze contracts. These were contracts for some trading between different companies, and they have analyzed those trading contracts, whether they have any loopholes or whether the contracts have any issues where it could end up that the contractor is not being paid, stuff like that. Dead ends, I'm not sure whether this would be a software artifact. So usually it's something that comes out of the software, some document that you can analyze. Software testing, this is where formal methods can be used. Yes, what? But we said software testing, we're just going to write some tests, right? So how are we going to use formal methods for software testing? So one example is we can let the software write test cases for us. So automatic generation of test cases, this would be based on formal methods. You have to analyze the software and then come up with some systems how you can test the software. So that's one thing. Other things are, there is which is somewhat related. There's this abstract interpretation of programming code where you can check whether you have any conditions to satisfy to reach some parts of the code. And that's actually, so one of the very common artifacts of formal methods in software, this would actually be programming code. There are lots of tools that try to analyze programming code. For example, whether there are any issues in the heap memory. So there are lots of tools that do that for your programming code. We said last time that these tools cannot be complete because of the this issue that we have if we have a Turing complete language, then there will always be analysis problems that no computer will ever be able to automatically do. But even then, there are some formal methods tools that help a user to do them, even if they can't do them alone. So there's lots of areas. Another artifact would be configuration files, right? Like these security configurations of your Amazon web service platforms. You would also use formal methods to make sure that they don't have any issues in them. So there's a wide range of things that we can analyze using formal methods. And it's not just always the obvious thing like code or models. This is the overview of what we're going to do. So we are currently here, and in 2 minutes we'll be here. We will start with the first chapter, which is declarative thinking, which is kind of a bit of motivation again, although we already started somewhat with it. Then the next thing will be so it's like this is the introduction chapter, so we're somewhere in here. Then do we start with this today? I'm not sure. SAT solving. So we will look at a tool to actually solve problems in some very small specification language. So we'll start with a simple specification language, and we will be able to solve problems in this language. We will use a tool for that, and then we will see what our applications where already this tool that we have, the SAT solvers, can do the analysis that we want. And there are already quite a few practical applications that we can do just based on SAT solving. So that's quite powerful. And then we're going to step-by-step extend this. So the next chapter we're going to look at is SMT solving. So this extends this kind of specification language by adding more possible things we can express in our language. So in SAT solving, we can't really talk about real numbers. In SMT solving, we can talk about real numbers. So everything that has numbers, we probably want to go to something like SMT solvers or other kind of solvers that are just specific for numbers. And then we will look at the specific tools. Z3, that's the one by Microsoft, which is like one of the most popular ones for general purpose applications. And then we will look at ways to apply this, for example, in code analysis. Then relational modeling. So this is a specific first order theory. So we will see what this first order means. And then we will look at a very specific one, which has a dedicated, basically language. So this SMT is more like a general purpose language. This one is a more dedicated one for a specific theory here. We will see that there is a tool, and actually this tool resorts back to SAT solving. And then we will see the different application areas. So the more we go along here, the more specialized we become. And then in the end, we will look at the temporal aspect. So how can we actually check also temporal behaviors and analyze those kinds of reactive systems. We will also start exercises that cover each one of those chapters that introduce a new specification language and tool. These exercises, so for each one, there'll be roughly 2 exercises. One exercise will be you use this tool manually, as is. And the second one, you use this tool programmatically. So you're trying to actually generate a specification that then the tool solves. So you're using the tool as like a backend solver. You're integrating this tool into a software system. And that's basically for, yeah, all of them. Yes, and as I mentioned last time, the way that this module will be assessed is by a project. So you have to pass the homeworks, but then to get a mark, you have to pass, well, you have to do the project and submit the project. And the project will be applying one of these tools to, yeah, solve some automated to automate some software engineering problem and solve it with this tool. So you can see the first homework will always be using the tool manually, and then the second will be automating the use of the tool. So the project will basically always be some more complex thing like the second homework in each chapter. So in the end, your project will be the automation of one of these tools in the context of solving a software engineering problem. And there's a catalog of there will be a catalog of projects, and yeah, then you can pick one, and this is what you can work on. I think we said teams of 2, right? Yeah. Okay. Great. Okay. Any questions about this? Great. Then we can go to the first real part. So let's have a look at this declarative thinking. We talked a little bit about specifications, but there is actually, I don't know, who has ever written a specification? So who has ever written a program? Good, yeah. So there is some difference between the way we usually write programs and the way we write specifications. And the first thing we need to maybe look at is declarative versus imperative. So there's also in programming, we have this declarative programming. In declarative programming, what we do is we express the logic of a computation without the control flow. So the control flow is usually how do we do something? How is it done? What is the first step, the second step, the third step? This would be like the control flow. If we do declarative, we just say what we want to be done, but not how. We don't care. The compiler or something else will take care of this. In imperative programming, which is a subset of most of the programming paradigms that we have right now, right? So object-oriented programming is kind of based on imperative, or imperative is somewhere embedded in the object-oriented programming. So there, we actually use some statements that modify the state of the program. So this is the most common thing. We have a bunch of lines, and then each line does something to our program, right? There are other paradigms, but now maybe those are the easiest to contrast. So other paradigms, anybody knows other programming paradigms other than, imperative, declarative? Well, we have object-oriented, we have functional programming, stuff like that. But yeah, let's focus on these two and contrast these two, because imperative is the most common that everybody's kind of used to, and then declarative, I think most of you also are used to declarative, but maybe you just need to see what declarative really is. Okay, so let's look at an everyday example, ordering a table at a restaurant. If we want to do it in an imperative way, then we basically have to say how we want to do it. So we could say, well, I see a table located under some sign, the gone fishing sign, that it's empty, and we're going to walk over there and sit down, right? This is step-by-step how you might do it. The declarative approach is you go to someone and say a table for 4, please. Then it's just what is the outcome that you want. So you just say what you want, and you expect that somebody understands what you want, and then how to actually translate the thing that you want into imperative steps, right? Because you still probably have to walk over to that table and sit down there. So another way, you tell somebody, well, I'm at this one location right now, and how do I get to your house from here? What would be an imperative approach? Well, this depends where your house is, right? But let's assume, I mean, it would be maybe a bit too easy if your house was in the student dorms right next to Aldi, right, next to the mall. But yeah.
Describe step by step where to walk.
Yeah.
Declarative would be the address.
Exactly. So yeah, exactly that. So you could write, yeah, go out at the north exit of the parking lot, take a left, then drive this street, stuff like that, right? The other way is, well, you just say, what's the address? Very good. Now, for the what do they have in common? So we have usually some kind of imperative abstraction because something has to do these steps. So if we have this declarative response, the table of the response would usually be something imperative. Somebody would tell us what are the steps to do this. Or if you just say the address, you know that this person you're telling the address has probably some way to convert that into some instructions, maybe by using their GPS that tells them the imperative abstract steps. Okay. Now let's see if we can detect what's imperative, what's declarative in some statements. So I have to disable this one. That's not quite right. Wait, let me. Okay, so just select the ones that are declarative here. So first open the browser, then type Google, enter imperative, and hit search. So don't actually do this. It's just the example, right? The next one would be find the definition of declarative. And then there would be one, before eating, mute the microphone. So this would be maybe more applicable for online classes, but yeah. Okay, so we have some majority vote that says B is declarative, because it just says find the definition of declarative. It doesn't tell us how. And A is not declarative, because A tells us exactly the steps of how we're going to find the definition of imperative, right? So, I mean, A and B, are they very, very different? Well, one is imperative, the other one is declarative. What is another difference in terms of, we said that usually the declarative stuff has an imperative translation, right? So what would be some imperative translation of this B? Find the definition of declarative. So it would be A, but replacing this string with declarative, right? Are there other possibilities? Yes. Yeah. Well, what are other possibilities? You can use a dictionary. Yeah, this also gives you a definition probably. You can ask a friend. You can do all kinds of things, right? So the good thing about, yeah, well, is that a good thing or a bad thing? Depends. So if there's no internet, then you probably have to take a dictionary, right? But if there's no internet and you have the imperative version, you don't have a solution. So the declarative allows you to find multiple solutions often, when the imperative sometimes only gives you one solution, and that's all, right? So there is some benefit of the declarative. And another thing is, maybe that's more related to software engineering, the declarative, we sometimes don't even know all the details of the system, but we can still write what we want. And then there might be multiple ways to satisfy this thing that we say we want. And we should be happy with all of them because we only stated what we want, right? So this is a benefit if the system doesn't even exist yet. Then I can still do it declaratively, but imperatively, if I don't know, am I going to build a browser or not, then it's a bit more tricky. Okay, the last one is a bit more unclear. Is this declarative or imperative? So before eating, mute the microphone. Why would it be imperative? It has some, well, instruction or condition, right? That's a bit, this looks like there's a chain of things here, right? But that's also fine for declarative. So declarative can be more complex. Before eating, that's like maybe a temporal thing or even a conditional thing, right? We don't even know is the person going to eat, but in case they do, then they should mute the microphone so that we don't hear them, I don't know, eating their crackers or whatever, right? So I wouldn't say that this like condition that puts it either as a conditional or temporal thing, that doesn't make it imperative, right? Mute the microphone, is that imperative? It could be that it's a single atomic step that works the same for everyone. Then you could say it's imperative, right? Because even a system out println hello world, still imperative, although it's just a single step, right? But if muting the microphone might be different or might be a more complex thing, then this would suggest that this is declarative. So now I would say that maybe you have your microphone mute button on your headphones or a keyboard shortcut, or you have to click on the screen. So I would say that C is quite declarative. Yeah. Okay. Then let's look at maybe declarative programming languages, right? So, or well, not programming, but any languages, any computer language that you know that is declarative, if you know any. So a language where you can express things that you want to be done or things that you like want to be stated, but not like how it's actually done. Okay, yeah, so we're getting some good answers in, and people are typing Python differently, maybe one's with a space afterwards or not. Yeah, this one has the space. Okay. Yeah, so the first one, SQL for databases, you say what you want to be done, but you don't say how it's actually looked up in the database and stuff like that, right? So that's clearly a declarative language, and that's also on the next slide as an example, I guess. Then Java, Python, Java, yeah, all these languages, Pascal, I would say they are rather imperative languages, because you really have to say how you want it to be done step by step. Of course, you could maybe have elements that are declarative embedded in these languages. That's also possible. So we will see some example. Maybe if you want to filter arrays or lists in Python, you usually write some function, what's the criterion that you want to be filtered, but you don't have to write the filtering algorithm, right? You don't have to loop over it and add it to a new array when you find it. So there are declarative aspects in those languages, but the language itself, I would say, is imperative. You have to write down statement by statement. Yeah, ChatGPT, that's more a tool than a language, but the language that you would use for ChatGPT would be natural language, right? You would use well, English probably, or some other language. And then, of course, you can formulate things that you want to be researched or things that you want to be well executed. There are people who actually used ChatGPT-like models to connect them to web services to actually have an impact on the real world. So if you tell it to, I think they used it for in some bio labs to automate the machines in the lab to synthesize some new proteins and stuff like that. It's a bit scary to let some AI synthesize stuff in your lab, but yeah, that's what they did. So there were some early papers about doing that. So yeah, you can use then ChatGPT as a kind of declarative front end. Okay. Yeah. So those are some examples. Here are some more. Yeah. Database queries. So you just maybe select over some table, and you have some criterion that you want to be satisfied, and then you just execute this statement, and you don't have to say how it actually does that. You just rely on that the implementation knows how to give you what you want. Another declarative language would be HTML. You have some tags where you declare what the elements are. You say, well, this is a header, this is a heading. Not sure that the heading should be inside the header. It should be in the. No, that's not. That's the header of the article. That's not the head of the HTML page. Okay, so header, yeah, header is different from head. Okay, and then you have a paragraph. So all these are statements that say, I am now describing an element of type header. I'm inside an element of type article. But how this is actually rendered, this is something that some rendering engine for HTML has to take care of, right? We don't know yet whether the text will be side by side or yeah, in which way. So that's declarative. We just say what's the kind of thing that we expect. We expect that one is the headline, and it should be rendered like that. And then the web browser is responsible for doing that. So it's another declarative language. Then even inside the same language, you can have a declarative and an imperative style. So that's this kind of what? Where are we? There's this kind of yeah, creating or maybe yeah, creating a list of what is it? Uneven numbers. So if there is a remainder after dividing by 2, then we should edit. So odd numbers. We're creating a list of odd numbers. And the declarative version would be on the right, where we're just saying, well, give us a collection where all the elements satisfy this property, compared to we actually going over this filtering the collection. Okay. So yeah, very different. One is really changing the state in every execution step in some loop, and this one really just says, well, do this filtering for yeah, for me. Okay, so in declarative programming, just the same slide. We express what we want without giving the control flow, and in imperative we do this step by step, giving the control flow. So now we're looking a little bit more at declaring and a modeling mindset. So what would we want to specify? We need to specify what can the system do, what behavior is allowed, what behavior is not allowed. We could again do some safety, some liveness properties, but in general, right? What do we want the system to do? What do we want it not to do? And we also need to usually talk about the environment of the system. So what can happen in the environment? What cannot happen in the environment? So if you want to specify some behavior of a robot delivering things to different rooms, then maybe we have to know about the environment, whether doors can be closed or whether doors will always be open, right? This would be important to know, because the implementation of the robot might depend on whether doors are open or closed. Yeah, then the execution basically would be we say what the system, what the program should do, and what is So we basically check what we specified. There we said what the program should do versus what is possible in the world. So this what is possible in the world with respect to the environment that we just described. This is what we do in the kind of checking of violations of the properties of the world. If we would have a program, we would simply run it maybe in some instance of the world, right? Different test cases might be different instances of the world, where each test case kind of simulates a world where that program operates in. But if we want to do it declaratively, then we really have to check the complete behavior against the complete possibilities of what could happen in the world. And the challenge here is usually that if you don't assume that something could go wrong, then the tool will maybe make it happen. So we had a very simple example of we wanted to program declaratively a robot that should not hit any obstacles, but it had a sensor to detect walls, right? So what you expect is you write the declarative specification, you press a button, and something comes up with an implementation of the robot. And if the robot sees a wall, it might turn around, right? Now, we know that this probably works. If you give it to a computer, the computer has no clue because the computer just says, I have a sensor to sense obstacles, but I have no knowledge about this obstacle myself. So what could happen is you could then ask the tool, okay, what's the reason you can't give me an implementation? And the tool gives you a scenario where the robot encounters a wall and the wall follows the robot. So if the robot tries to back up, the wall still follows the robot. Is that realistic? Not really, because we know that walls don't move. So we have to add usually this kind of assumption to our validation check that we can say, yeah, actually walls, they don't move. They are stationary. So if you, as the robot, move, the position of the wall will not change. And that's important because you can find all kinds of bad behaviors that an automatic check against any possible world would give you. And usually you have to be this kind of pessimistic. You have to be pessimistic in the sense that whatever could go wrong will go wrong, right? Because you want to ensure that you handled all these cases so that your software works in the worst case scenario. And that's why you have to exclude some scenarios that are not realistic, like that the wall follows the robot. And we will see this maybe only in the last chapters, where it's really a bit more important to model the environment. So the difficulty is then to come up with these assumptions. Why is that difficult? Everybody knows that walls don't move, right? But would it have been the first thing you write down when you want to specify your robot behavior? Probably not, because if you give a specification usually, or if you give a set of requirements to a human developer, then this human developer probably has some shared understanding of how the world works, right? If you're from some very particular domain, maybe you work in chemistry or biology, and you have some requirements that you give to a software developer. All this software developer ever did was study, I don't know, electrical engineering and digital engineering. This developer might not have all the implicit knowledge that the biologist had who wrote the requirements, right? So there you already have this kind of challenges where there might be some assumptions that, of course, the biologist knows, but never wrote them down because they're so natural. And that's the same thing for us, well, humans. We have some assumptions about how the world works, and we usually don't write them down because they're natural to all of us, but they might not be natural to a computer. yeah, and there's also research on that. So there's research on how do we actually come up with assumptions that people are bad at writing. Yeah. Okay. There's some very nice, funny game. I think it was in a some kind of hackathon where some person developed this game. It's called Baba is You. The link is here. There's a commercial version, but there's also the original version of the hackathon. So if you want to play it, you can use the original version of the hackathon, which is free. It's learning how to write declaratively. So yeah, I played it some time ago. It gets more and more complicated, but it's about writing declaratively the steps that this Baba figure should do on the screen. Okay, yeah, but now we're going to look at something more serious, and that's propositional logic. So propositional logic is really easy, and I guess most of you know it. You have some propositional atoms or variables, and all they can be is either true or false, right? So you have some variables, P, Q, R usually, but you can give them any name, and they can only be true or false. And you can make statements with these variables or formulas by using some operators. You have the negation operator, the conjunction, disjunction, implication. We already used this in the last session, right? When we tried to formulate this John being late and at the train station, the train being late, we already use propositional logic, right? So I guess most of you know propositional logic. The reason why we're just repeating it is so that we have a common understanding or know what these operators mean, know what we mean by well-formed, for example, because that's not so common. So some formulas are well-formed, and some are not well-formed. So formulas that are not well-formed, we would say they don't make sense, they're syntactically invalid. So how can we have some well-formed rules? There are some simple rules. If these are variables and then these are formulas, then the negation of a formula is well-formed if the formula itself was well-formed, right? So if you have some statement and you negate that statement, then this is still well-formed if the original statement was well-formed. If the original statement already had some issues, it wasn't well-formed, then also the negation doesn't make sense. Okay, so conjunction, yeah, you have to put one thing on the left, one thing on the right. And if the thing on the left and on the right are well-formed, then also the conjunction is well-formed, right? So yeah, for the and, for the or, the same, for the disjunction, we have either this or that, and then both of them had to be well-formed. So that's hopefully very simple rules. The implication, very similar. And we used all of these, did we use all of these operators? We used the and. For the John example, we used did we use implication? Maybe. And the negation, yeah, we also use that. So you already know these kind of operators. Is there any question about this? We will look at some examples. So and although I had the rules about what is well-formed on the previous slide, you could probably also just follow your intuition. But if you want, you can check the rules again. So you will have these formulas, I think, on your screen when you open the question. So I'll just put the well-formedness rules here, and then maybe I'll just to see how many answers we got. Oh no. Okay, so yeah, let's look at these. So now, how would we even decide whether something is well formed or not? So let's look at the first one. I don't know if I can zoom. Yeah, okay. So let's look at the first one. The well, some majority says well, minority says that they're well formed. How would we check this? So if we would go by these rules, we could try to identify, build the formula up from basically from starting from some one rule. We could either do well bottom up or top down, right? Doesn't matter. So let's say we go, I don't know, bottom up. So let's start with a most simple formula that already uses one of these operators. So let's use this one. So P and Q, that's the left side of the formula, right? So now that is well formed because it fits directly into this schema, right? So this side is well formed. And now let's plug that in again here on the left side. And then on the right side for this psi, we just use R. And then we have this formula. So it is well formed because we can construct it based on these well formed rules. Okay, so next one, this one, or let's look at the more easy one, D. P and Q implies R. We can construct it again in the same way, right? Now, what about B? Some people here must think that it's well formed. No, not well formed, right? So there's some people who say it's well formed. Okay, who says it's well formed? Yeah, can you explain why?
Negation.
Yeah, so of course negation, we can apply this twice, right? Because if it's after applying once, it is well formed based on this rule, and then we can just apply it again. Yeah, and then, I mean, here, this is slightly different because we have an or instead of this end, but of course we can construct it the same way. So yeah, this is also well formed. Let's see, do we have the, yeah? It's, yeah, maybe it's meaningless, but it's allowed, right? Yeah, yeah. Two negations in propositional logic, they would cancel out, right? But still, it's syntactically just it's well formed. Then C, we have the lowest in terms of well-formedness, right? And yes, C is not well-formed. And the reason is here we have a negation that doesn't negate a formula. So because here we have this negation in the end, and negation alone is not a formula. So you can't plug this negation alone here as an element of this, and you can't also have the negation follow something. So you can't have the negation follow Q. You also can't construct this with this negation formula. So here, this one is not well formed. And the reason why we're interested in well-formed stuff and not well-formed stuff is that, well, do we have something like that in programming languages? Well-formed and not well-formed? Yeah, it's the syntax error. The compiler or interpreter will tell you you have a syntax error here. And that's exactly this well-formed or not well-formed. If it's well-formed, then it compiles. If it's not well-formed, we don't know what it even means. So yeah, and exactly, yeah, that's why we're looking at this. It doesn't really, we can't really assign it a meaning if it's not well-formed because it doesn't follow the rules that we set for our language. The rules for, let's say, Python or Java are much more complicated than the rules that we have here for this propositional logic, but there are similar rules that correspond to this, and we have similarly well-formed and not well-formed. Okay, so usually you give languages as grammars, not as these kind of declarative rules. Well, grammars are still kind of declarative, but you can derive stuff from grammars. So we could also write it as a grammar like this. So these are the ways to construct formulas. You either have some propositional variable, or you have this negation of a formula itself. So here this is very maybe a bit strange in grammars, that basically the symbol here appears on the left and right, but that's not like a definition of the symbol. It's more like any formula here can be used with the negation sign. And then usually, if we want to give meaning to something well-formed, it's also really important to see the binding or precedence of the operators. So which one is stronger? Which one do we have to evaluate first? And then here, the way we have to evaluate it is the strongest is always the negation. So the negation will apply to the element that is immediately after it. Then the next strongest in binding is the and, then the or, and then the implies. So yeah, this makes it then possible to see what are possible equalities. Let me just, this is getting really big. So yeah, let's just look at the correctness, then lock it and go to the next one. So now, what do you have to do for this question? Maybe I should put the previous slide. So the order of the operators. So let's maybe do the first one together. Here we have P, or, Q, and R. So now on the right side, it is written with parentheses around the or. This would only be correct if the or is really binding stronger than the other operator afterwards, right? So here, for this one and that one, for left and right to be equivalent, we would have to make sure that this or is really stronger than the and. Because the alternative is that we have P, or, and then we open the parentheses, Q and R, right? The binding of and is stronger than the binding of or. So what would happen is we first have to kind of evaluate this and only then we have to evaluate the or. So this means that this one is not a correct equality. And that's basically how you do it. You just check, do these parentheses really reflect the precedence of the operators? That it really puts the strongest one first. So if you look at, well, exactly the same example here, right? P, or, Q, and R, the end is stronger. So here we would have that this one is actually correct. So then let's look at, yeah, second one is correct. First one was not correct. We can also look at the solution. Third one, the C, we dropped the double negation, right? We can do that because it cancels itself out. And then the next strongest thing would actually be this and again. So yeah, here, P and Q would be stronger than this Q or R. So the or R is just attached at the end. Then D, we have something that is not correct. So here it says that the implication basically binds Q and R together. But that's not correct because we have a conjunction here that binds P and Q stronger than the implication. So we would have to do P and Q first and then implies R. The safest thing, if you don't know about how strong each operator binds, just use parentheses, right? But sometimes if you have too many of them, it gets not so easily readable. So that's why you can rely on this strength here of the binding of the operators. Okay. Yeah, then there are some abbreviations that you might find sometimes. So when you see maybe some more scientific papers where people don't have many pages, the publisher says you can write 10 pages of your paper, and then people say, well, I'm going to abbreviate everything as much as I can. So instead of this grammar here, like this much nicer one, right? They write the same thing. They say, propositional logic is defined like this, only 3 terms. How come? Because the rest is just syntactic sugar. So you can use negation and disjunction, and with that you can construct your own conjunction. So how do you construct a conjunction? How do you say that this basically psi and this psi, right? Psi and phi. You can write it with De Morgan's law as basically not psi or not phi, and then negate that thing. And with De Morgan's law, you will end up with this. So this is just a shortcut where you only have to define those, well, 2 operators basically to end up still with, well, implication. There's also an important one. Implication is basically negation of the left or simply the right. So this one is extremely common, and yeah, you might come across this many times. Okay, so now that we looked at the language and which operator binds stronger than what other, we need to look at what does it actually mean. So what can we do with our formulas? And we give a meaning to the language that we have just looked at by saying that, well, actually, we want to assign truth values to our formulas, to well-formed formulas. They can be true, false, and we want to have a valuation of a model, which is basically, so a valuation is now an assignment of each propositional atom to a value true or false, and this leads to a truth value of the formula. So if we say evaluation, that's simply assigning each variable a true and a false, or a false. And then we can define something like semantic entailment. So this models operator here, we can say that this set of formulas here on the left models the formula on the right. And the meaning of this is defined as if all the valuations where the elements on the left evaluate to true, then also the formula on the right must evaluate to true. So let's maybe do a very, very simple version where we have where these psi's here are just variables. So if we have a, it's better to write this down. Okay, so if we have a comma b and they're just propositional variables, and we say this entails some formula, what would be a good formula? A and b, okay. A and b. I'm just going to write the end like this, right? Okay, so now we have here on the right side our formula, and we have this 2 formulas on the left side, right? Now, is this semantic entailment true or not? So does A and B model the formula A and B? So now we look at the definition here. If A and B evaluate to true, then the right side formula evaluates to true. So we can now simply plug in true into the right side formula, right? So let's do that here. So we end up with true, well, and true, right? And that is true. So the variables A and B, they semantically entail the formula A and B. Now, is it still the case? So we follow again this definition. If this, I mean, now the simple thing is that we have the same formula on the left and the right side, right? So if we said any valuation for making psi true, that's very simple because that's A equals true, right? So A equals true and B equals true. We know that because that's on the left side. On the right side, we have A, and A by definition is true. So this is a very, very simple semantic entailment. Of course, if we have something on the left that we already know is true, and we have that same thing on the right, then it is a trivial entailment. So here, yeah, that's also a semantic entailment. Now, let's do A and B. What do we have now? No semantic entailment because if we set A to true, it doesn't guarantee that the formula A and B will be true because B could still be false and then A and B is false. So no semantic entailment here. So, okay. Now, yeah, how do we usually define the operators? Maybe you've seen this before, truth tables. So if for the conjunction to be true, both left and right side have to be true. For and it's false otherwise, right? And for the disjunction, it's enough if one of them is true. Both of them true is also fine. But if both are false, then the operator will also evaluate false, right? Then implication here, if the left side is false, implication always is true. That's a good thing to remember. So false implies everything. But then if the right side is true, you also need the left side to be true. Negation just flips the values of the inner formula. True itself is always true, and false itself is always false. Okay. Now let's look at some semantic entailments. Now we have a little bit more complex formulas that we write on the left and right. So in the mini example, I just had individual atomic propositions as formulas on the left, but now here you also have, for example, the negation of some variable. And what does this mean if the negation of the variable is on the left side? For semantic entailment, we have to make sure that in case all the elements on the left are true, so how do we make not P true? Is there a way to make the formula not P true? By setting P false, exactly. So we know that here there's only one way to make it true by setting P false, and there's only one way to make this one true by setting Q true. So P is false and Q is true, so we have false and true. What does that give us? False and true gives us false. We negate false, we get true. Okay, so this means that this is a true semantic entailment. Okay, so B nobody likes, because we're basically only saying something about P. We have no clue what the values of Q and R could be, right? So let's see if we have now what do we have to do to see whether this is a semantic entailment? We have to check. We know that P is true, right? Because it's on the left side. Okay, so P is true. We have for Q and R, we have to check all possible values. How many are there? For each one, just two, right? True and false. Do they have an impact? No, because we have a disjunction here. We say true or something else, but if one side is true in the or, then the value of the or is true, right? So let's see. Yeah, actually, they were all correct semantic entailments. So yeah, don't be tricked by some variable values having possibly multiple values. In semantic entailment, you would really have to check that it's true for all of them. And here, well, we could, of course, check it for all of them, but we can already see that we don't have to. But you would have to interpret this semantic entailment really for all possible values. And that's why we probably want to use a tool to do this for us, because, yeah, it gets a bit difficult to do in our heads at some point. Okay, so now let's look back at our example that we had in the last session. If the train arrives late, and there are no taxis at the station, then John is late for his meeting, and John is late for his meeting, and the train did arrive late, and therefore there were taxis at the station. So if we want to express this in propositional logic, we already did this last time. We basically assigned propositional variables. I think one for the train late, then for no taxi or taxi, and then one for John. And these were the three variables that we defined. And then each one we wrote in some sentence here. Okay. Then now let's look at the concepts of equivalence and validity. So we said we had this semantic entailment, right? And we can say that two formulas are semantically equivalent if one entails the other and also the other way around. So basically, this semantic entailment was whenever this is true, that must be true. And also the other way around. So whenever this one is true, that must be true. That's what we have written here. And then we say they are equivalent. So no matter how we put the variables, they will always agree in the truth values. So basically, by doing semantic entailment both ways around means that if one is false, the other one also has to be false. Otherwise, one of these two would be violated. One of the two semantic entailments would be violated. And then if one is true, the other one also has to be true. And then we can write this equivalence, like that. And we can also now define a term called validity. So we can say a formula is valid if we don't need anything to make it true. So if it basically, no matter what the variables are assigned to, an arbitrary valuation makes this formula true. Maybe you heard of this term tautology. That's like if you have some statement that is true no matter what the variables are. And that's exactly what we now call in this context of propositional logic, that's called validity. Okay. Now, if we want to select all valid formulas, maybe we can just simply discuss this. Who thinks that number one is a valid formula? So we have P and Q not. So now the question is, how do we check whether this is a valid formula? We would have to check that all assignments to P and all assignments to Q, we would always have to make sure that we end up with true for this formula, right? Okay, so that's a bit, so let's say false and false is false, negation, it's true. So now we have one assignment checked. Do we check all of them? Or do we do it the other way around and try to find one where this formula actually evaluates to false? So if we find a single example where this formula evaluates to false, we know it's not valid. Okay, so somebody has an example where this evaluates to false? Yeah. So if P is true and Q is true, then we have true, we negate true, we end up with false. So no way this is valid because we found an assignment where it's not true. Okay, so it's not a valid formula. Now, valid and well-formed are very different, right? Because well-formed was this syntactic property that we can interpret it, and valid now is a semantic property that no matter what we assign the variables, no matter what valuation we give to them, we basically have a true value. So what about this one here? Can we find again an example where this evaluates to false? This one is valid. Can somebody give an intuition why it's valid? So the insight is always false because we have P and not P. So if we say P is false, then not P is true, right? But that's a conjunction, so this still remains false. And if we say P is true, then not P is false, and this conjunction makes it again false. Then we negate it, and it's true. So no matter what we assign to P, it's always true. So we have a valid formula. Last one, double negation of P. Is it valid or not? Not valid because what is an assignment where this formula is false? False. False to P, then it's false. Yeah. Very good. Okay. Now, how do we get from semantic entailment to, sorry? The first one was not valid, right? Right, yeah, because we found a way to make it false. Then the last two, well, only the middle one was valid. And the last one was again not valid because we found a way to make it false. Okay. So then there's a relation between semantic entailment and validity. It's a little bit, yeah, complicated, but basically we have here the semantic entailment, right? So how can we check the semantic entailment? We can check it actually by checking validity of this formula. So if we want to check the semantic entailment for some formula, we can reformulate it into this structure where we have all these implications which are then nesting the formulas, and then we just have to check that that is valid. Okay, so how would we do this for our example here? Here we actually want to know whether the first, the second, and the third semantically entail the fourth. So we want to write basically this statement 1, statement 2, statement 3 semantically entails statement 4, right? Because we said number 1, 2, and 3 are the general rules. They have variables in them. And we want to know whether number 4 is a valid conclusion. So this conclusion is true no matter what situation happened, whether it was whether the train was late or whether there were taxis. Then we want to know, is this a correct semantic entailment? So basically, we could formulate this as semantic entailment. 1, 2, 3 entails 4 as this implication here, and then check it for validity. So if we prefer validity checking over semantic entailment checking, then we can do that. The other way around, of course, if we have something that checks semantic entailment and we want to check validity, then we can also, yeah, do it because it's an if and only if. So we can choose whichever one we prefer. in practice, we will see a way that validity is actually quite easy to check. Yeah, we will see why. We already applied this trick, right? We check validity by trying to find an example where the formula becomes false, because then we know we don't have validity. And this means we only need a single example to prove that we do not have validity. And the absence of any single example basically means that we have validity. So if we would have a tool that finds an example, if one exists, then we can easily check validity. And now we know, based on this relation here, that this validity checker allows us to check semantic entailment. Okay. Now, this relation between validity and satisfiability. So we say that a formula is satisfiable if it has a valuation that evaluates to true. And we can use this basically, yeah, if it is satisfiable, or a formula is satisfiable if the negation of the formula is not valid. That's exactly the same relation. Now, if we negate a formula and it is not valid, this means that there is some assignment to the variables that makes the negation false because it's not valid, right? And this assignment to the variables of a negated formula that makes it false, that's an assignment that makes the original formula true. So we exploit this relation between validity. We just use some negation, and then we can get satisfiability. Of course, we know that satisfiability is the much easier thing to check, right? Because we just find, in whichever way, some example. So usually, you put the negation from here to there, and you say it's not satisfiable if not the formula is satisfiable if it is well, the negation. Can we move it over there like that? We probably have to do the double negation, right? Because this is not valid. So what we do to check whether a formula is valid, we check that its negation is satisfiable. Yeah. So we basically have to pull out the not from here, from there, and move it to this formula. So if the negation of the formula is satisfiable, then we know that the formula is not valid, right? Because this means we have the negation of the formula means we found something that makes it false, and then it's not valid. Yeah. Okay. So we only move the negation. Okay. A bit tricky, yeah, but this is what we will use later on to check validity. We will basically negate the formula, check if it has an assignment, and if it does have an assignment, we know the original formula is not valid. Okay, and the first tool, we will see it in the next session. So the first tool we will have is a tool that can actually check this satisfiability and validity for us, so we don't have to do it manually anymore. So the next session is it Tuesday? Yeah, okay, so yeah, see you on Tuesday.